Hi there, welcome back to MathSub's YouTube channel. In today's video, we will be talking about real numbers and some related concepts like properties and operations of real numbers. Let's get started. Before talking about real numbers, we always need to go in the order in which we understand numbers, right? So numbers always come in a set of ideas known as buckets. Like there are different buckets of numbers, right? The first bucket is a natural number. These are all called natural numbers. And then we have whole numbers. Okay? And then we have integers, right? We have integers. And then we have rational numbers, right? We have something known as rational numbers. And then we have real numbers. And then we can even go further from there to imaginary numbers. Imaginary numbers sounds spooky, doesn't it? Like they're imaginary, like imagined for some reason. They are not really imaginary, just that the way we understand them makes them look like they're imaginary. So the idea here is, as you go down this bucket, the bucket gets bigger and bigger. The natural number bucket is the smallest bucket. And as you go, this bucket is slightly bigger than this, right? Just one number is extra. So if you talk about natural numbers, what are natural numbers? You start with 1. It's a positive one. They're all positive, right? They're all positive. Start with a 1, 2, 3, 4, and all the way up to 989, all the way up to whatever, and then infinity. Right? Infinity is the largest possible number you can think of, which you won't be able to think of. That's why we gave it a number. That's why we call it infinity, and we don't say it's x or y. Now, whole numbers is just one number more than this bucket, or in mathematics we call it a set, right? Each of this is a set. Each of these are known as sets. This is a set of natural numbers, the set of whole numbers, the set of integers. Each set has a lot of numbers in it, but each set is bigger. As you go down this range, you get a bigger set. The set keeps increasing in size. So, whole numbers have just one number more than natural numbers, which is 0. Is the only number extra, and then everything else is a natural number. 0 plus natural numbers. So, whole numbers have one number extra compared to natural numbers. Now, what about integers? The set gets even bigger. The set gets almost doubled, in fact. So, integers are all numbers which integers are basically a mirror image of all the natural numbers plus the natural numbers, right? So, if you start with 0 and 1, 2, 3, 4, and then you go to infinity on one side, you also need to go to the other side, right? So if you put a mirror at 0 and everything else is reflected, you get a -1, you get a -2, you get a -3, and all the way up to the other side of infinity, right? So integers is a set which contains all the whole numbers plus all the inverses of the natural numbers, like -1, -2. And that's why this set is almost twice as big as this set. And now we go to rational numbers. Now, what are rational numbers? Understanding the idea of rational numbers is quite crucial for you to be able to do well in any math exam. So rational numbers are any number which can be expressed as p by q, where both p and q are integers and q is not equal to 0. Both p and q are integers. That's a crucial property right there. So any number of the form, let's say 3 by 2 or 5 by 7 or 100 by 121 are all considered to be rational numbers. It could also be written as 1.5. It could also be written as 5 over 7 is 0.8 7428 14285 714285, and then whatever that is. So basically all the numbers in between the numbers of integers, right? So if you think about where 1.5 is, 1.5 lies somewhere in between 1 and 2, correct? Or 0.714 lies somewhere between 0 and 1, correct? So integers have these rational numbers in between them somewhere. So rational numbers are a set of all the numbers, including integers, and all the numbers in between integers as well. So if you can now imagine any number like 1.284, 1.284, but it has to stop somewhere. So that number is somewhere between 1 and 2, right? So all those numbers you can imagine between 1 and 2 are also part of rational numbers. Integers plus a set of other numbers is rational numbers. So rational numbers is a much bigger set, much bigger set compared to integers. This is already double the size of this, but this is way bigger than this. And now what about real numbers? Now what other numbers could be there, right? We've imagined a lot of numbers. We also already said that imagine all the numbers between 1 and 2 and 2 and 3, and all of them are part of natural numbers. But there are a lot of numbers which cannot be expressed as p by q, where both p and q are integers. There are a lot of numbers which can't be expressed like that. So for example, a number like pi, you cannot write pi as a p by q format. It's perfectly as two integers, you won't be able to represent it. Or a number like root 2, or a number like root 10. So these numbers are not integers. You can write root 2 as root 2 by 1, but root 2 by 1 is not a rational number because the p by q format needs to have both integers, right? But root 2 is not an integer. It's a square root which is not a perfect square. It's also called a surd. So numbers like this, including all the rational numbers, are the set of real numbers. This is a slightly larger pi it's a much larger pi compared to rational numbers even. So real numbers are all the numbers, including rational numbers, which cannot be expressed as p by q format, where p and q are both integers. Now imaginary numbers are not part of our syllabus, so we don't have to really talk about them here. But so basically imaginary numbers include those numbers which can't really be represented as a root 2. So for example, a number like -2, when you put under a square root, you can't really calculate that using the conventional mathematics that you know. So what we do is we write a root -1 is equal to I. We have defined this value as a value called I, and we say that if root -1 is I, then what would root -2 be? What would root -2 be? Then root -2 would be -1 into 2. So if root -1 is I, this would become root 2I. So and then we've defined a set of numbers and we call them imaginary numbers. And mind you, there are set of numbers even beyond imaginary numbers called quaternions, and there is so much of math if you want to explore. But of course, we're not going to get into all that. This session is all about real numbers. Now, as you might have learnt in earlier classes, you know that all real numbers exist on a number line, right? And this number line is a very important concept because it helps you understand a lot about numbers without memorizing the properties. You can visualize how numbers work without really having to memorize the ideas behind it, right? So it gives you a visual tool to be used. So the first thing is, as you go towards the right, the numbers are increasing, right? The numbers increase as you go towards the right, and the numbers decrease as you go towards left, right? And if you want to represent any number, you can always drop in a line over here and write, let's say, a number like 1.1, or you can write a number here, let's say it's -1.8. So if you go towards the right, -1.8, if you want to know whether it's greater than 2 or less than -2, you always see which side of the line it lies on. If it lies towards the right, it's a greater number. If it lies towards the left, it's a lesser number. It might be confusing to see that -2 is actually less than -1.8, but since it's a negative number and you visualize it, that -1.8 is on the right side, right? It lies towards the right of -2, and that's what makes it a higher number. Now, even let's say a number like root 2. What is value of root 2? The value of root 2 is 1.414, and the value of root 3 is 1.732. You need to memorize these. These are very important values. So the value of a root 2 is 1.414, which lies somewhere about here, right? So it lies somewhere about here. So root 2 lies somewhere over here. And root 3 lies somewhere over here. So all these numbers are part of the set called real numbers and can be represented on a number line. So to say that any number n lies between two numbers is to say that it lies on the number line in between those numbers, right? So for example, if you say a number n, let's say a number n lies somewhere over here. Let's say a number n lies somewhere over here. You can say that the number n is less than 2 and it is greater than minus 3. So when you represent something like this, you mean that this number n lies somewhere in between these two numbers, right? So it's somewhere in this region. It could be minus 2.8, it could be minus 1.3, it could be minus 0.2, it could be any of these numbers. This is also representing a set. So when you represent something like this, you're talking about a set. You're talking about a set of numbers, and it belongs to those set of numbers which lie between minus 3 to 2. But they are not equal to minus 3 or 2. So if you want to represent it that way, you would represent it as minus 3 less than or equal to n and less than or equal to 2. In this case, this is a different set, right? This set includes the numbers 3 and 2 as well, and that n could be anywhere between minus 3 to 2, including minus 3 and 2. Great. So now there's another concept about absolute values, right? So an absolute value, what is an absolute value? An absolute value represents the distance of the number from 0. Right. So in this case, for example, if you take a number like, let's say you take a number here. Let's say you take a number here, like let's say is 1 minus 1.7. What is the absolute value? The absolute value is distance of 1.7 to 0. The distance, right? So how many units is 1.7 away from 0? It's about 1.7 units. So, and let's say a number here, like let's say 2.7. What is the distance of 2.7 from 0? How many units is it? It's 2.7 units basically, right? It's 2.7 units. So an absolute value of any number is always equal to the positive value of that number. The sign is disregarded, and that is the idea of absolute value. So the absolute value of minus 1.8 is represented this way. So when you see something like this, you mean that it's an absolute value. So it's always equal to the positive. It's always equal to only the value of that number and not the sign. You don't have to forget about the sign. So whenever you see a number like mod x, this is called a mod. This is mentioned to be as a mod. It's called mod of x. So if you have a mod of x or a modulus of x, we always need to consider the absolute value and not the sign of that number. So a mod of x will always be equal to plus x. A mod of z will always be equal to plus z. A mod of minus 3.2 will be equal to 3.2. A mod of 5 will be equal to 5. So a modulus represents the distance of that number from 0, irrespective of and that, since distance is always going to be a positive value, the mod of any number will always only be considering the value of that number and not the sign. Great. Now let's look at some important properties of real numbers. Let's look at some important properties of real numbers. So the first property we'll be talking about is the commutative property. It's called the commutative property. You don't have to worry about the name, but basically the property is very simple. It says that if you have two real numbers x plus y, it would always be equal to interchanging. The operation here will not really matter. You can always interchange these two values. You can say y plus x. So x plus y would be equal to y plus x. And the same idea also applies to multiplication, right? So x into y would be equal to y into x. So this applies to any real number, not just integers, right? So if you have a number like 5 root 2 plus root 2, this would be equal to root 2 plus 5 root 2. You can interchange it and you still get the same number, right? So for example, if you say root 2 is 1.4, approximately 1.4. So 5 times 1.4 plus 1.4, right? So that would be 7, right? 7 plus 4 is 8.4. And even in this case, it would be equal to 1.4 plus 1.4 times 5. That would also be 8.4. So this applies to any real number and not just integers, right? So even in the case of multiplication, if you take an example for multiplication, you would say, let's say 7 root 3 multiplied by 1 by 6 multiplied by, or we can just take two numbers, multiplied by root 3 by 6 would be the same as root 3 by 6 multiplied by 7 root 3. So real numbers give you the flexibility of moving around without having to worry about which number lies where. And this applies only to the plus, the addition and the multiplication bit. You need to remember that it's not going to be applicable for the subtraction, right? X minus y is not going to be equal to y minus x, and x divided by x by y is not going to be equal to y by x. It doesn't apply to these cases. It does not apply to the subtraction and the division case. It only applies to addition and multiplication. And this is known as the commutative property. It's called the commutative property. You don't have to worry about the name, but basically it's about interchange. You can interchange the numbers if you have an addition or a multiplication. Now the second property is known as the associative property. It's called associative property. So the associative property tells us that you can group numbers in whatever way you want and you still end up with the same answer. So you have x plus y plus z. You can either group it as x plus y first and then add z, or you can group y and z first and you can add it and you still end up with the same answer, right? And the same applies for multiplication as well. So x times y times z, you group them these two first, or you group the other two first, you'll end up with the same answer. So this property applies to real numbers and not just integers. We've already studied about integers. So if you take any real number like 5 root 2 plus root 3 plus 7 by 2 and you group them, and you group these two together and then you group these two together, you're going to end up with the same answer. So 5 root 2 plus root 3 plus 7 by 2 would give you the same answer, right? So the same applies for multiplication as well. So if you have 5 root 2 times root 2 times root 6 and you're able to take this together, you will end up with the same as 5 root 2 times root 2 times root 6 and taking this as a separate one. In this case, you'll end up with 5 times root 2 times root 2 is root 2 times root 2 is 2. So 5 times 2 is 10. So this will be 10 root 6. So in this case, you can write root 6 as root 2 times root 3. So if you write that, you will end up with 5 root 2 times root 2 times root 2 times root 3. And that would be written as 5 root 2 into 2 times root 3. And this would be written as 5 times 2 is 10. And root 2 into root 3 is again root 6. So end up with the same thing. So no matter which grouping you take, you will end up with the same answer. Again, this only works for addition and multiplication. It's not going to be working for subtraction and division. So be very careful while you're doing that. Associative property for real numbers only works for addition and multiplication. Let's go to the next. So in this property, if you have two real numbers which are multiplied in such a fashion, when you have xy and xz, you will be able to factor out the x and add the other two first and then multiply them later. This will be really handy in certain cases when you have to perform some difficult calculations. For example, if you have a concept like 784 times 26 and you have plus 784 times, let's say it's 74. So in this case, you might have to multiply this first and then multiply this first and then add them together. But to make it simple, what you can do is you can take this as the common factor and multiply 26 plus 74, right? And this would give you 784 times 100. And that gives you a much easier way to calculate. So you can use these properties to make your life and calculations and time easier. That's the reason we are learning about these things. And the fourth property is when you have two real numbers which are positive, the result is always positive. Let's say you have x which is positive and y which is positive, and you add them together, you're always going to be ending up with a positive value, is a positive number. So two positive real numbers when added together always give you a positive number, right? And two negative real numbers when added together always give you a negative real number. But if you add a positive and a negative together, you don't really know the outcome. It depends on the values, right? Similarly, if you multiply a positive and a positive real number, you'll end up with a positive real number. And if you multiply a positive and a negative real number, you'll always end up with a negative real number, right? If you multiply a positive and negative, you always end up with a negative real number. But if you multiply a negative and a negative real number, negative and negative, you end up with a positive number, right? That's the idea. That's the idea, right? So this is how the properties of real numbers work. Another interesting property which comes in quite handy is that if you know a product of few real numbers is 0, let's say you know the product of these numbers is 0, you can be sure that at least one of them is 0. There's no other possibility. At least one of them has to be 0. It could be 2 0, it could be 3 0, it could be all of them 0. At least one will be 0. And this can be used to solve a lot of problems where you know that the product is 0 and you can equate some of those numbers to 0 and to solve the question, right? So whatever number of multiplication real numbers you have, x into y into z into a into b into c, it does not matter. If you know the product is 0, then at least one of them is definitely 0. And the last property we'll be talking about is the property of inequality, right? So in this property, it's said that the modulus of x plus y is always less than or equal to the individual modulus values. So if you are adding two real numbers and taking the absolute value of that, it will always be either equal to or less than the modulus of the individual numbers. So if you take an example, you can very clearly see that. So if you take the modulus of 2 plus 10, this would be, if you try to calculate what is the individual modulus values, it will be equal, right? So in this case, you have modulus of 12 is equal to modulus of 2 plus 10. So 10 plus 2 is 12, right? So basically, in this case, both are equal to 12. But let's say you take a different example. Let's take a different example. So let's say the modulus of, so let's say x is minus 2 and y is 10. So in this case, what's going to happen? So you have a modulus of minus 2 plus modulus of 10. So in this case, you're going to get a modulus of 8, right? And this you're going to get a modulus of 2 again. So modulus of 2 is 2. Modulus of 2 is 2. And modulus of 10 is 10. And modulus of 8 is what? 8. So this value is less than this. So this means 8 is less than 12. So in this example, what you have seen is depending on the value of x or depending on the value of y, the overall inequality can shift, right? So that's why this property is important to understand, because if you ever have a question where you're dealing with moduli, then you may not be able to always equate it to in the individual modulus. You always need to see that the individual modulus are able to give you the result or not only after you calculate. So you first have to calculate it, only then you will be able to understand whether it's less than or equal to. So basically, when you have a modulus of a sum of two real numbers, it's always going to be either less than or equal to the individual moduli. It's never going to be greater than. The greater option is never possible, right? And that's it for today's video. Thank you for watching. If you like the video, please do hit the like button and do subscribe to our channel for more such interesting videos. Do share this video with your friends to help them learn about real numbers. I'll see you in the next video. Have a great one.